Welcome to another edition of Daily Airline News, focusing on the search for MH370. I am Jeffrey Thomas, and I'm delighted to say joined by my co-host Richard Godfrey in Frankfurt. Good morning to you, Richard.
And good afternoon to you, Jeffrey.
Thank you. So, viewers, Whisper for Experts, episode 217. This is the second of three presentations on Whisper in this series. The first episode was Whisper for, well, we did say dummies, but let's rephrase that, people of my intelligence. The second episode is Whisper for Experts. That's people like Richard. And the third episode is the 10 things you must know about Whisper in order to find MH370. This series on Whisper is part of our warm-up for the MH370 search, which is to restart in November. And we should see some movement of Ocean Infinity ships in a few weeks' time, hopefully as they track towards the search area. Let's cross our fingers on that one. We've been running a test separately on comments being deleted. So far, 150 viewers have taken part in the test and made a comment with the word test, and at the same time sent an email to Richard with their YouTube handle or username. The test will close at midnight today UTC, and the results announced on Saturday. And talking of Saturday, we're taking a day off tomorrow, and we'll be back on Saturday answering your questions on Air India, and we'll also have the results of the test. Now, before I hand over to Richard, just a quick message. Please subscribe to us, please like us, please support us, and thank you for those who are. Really appreciate supporting responsible journalism. Please keep those wonderful comments coming, and please keep those fantastic questions coming. We do appreciate them, although they do challenge us. Now, Richard, over to you for the Whisper for people who are more intelligent than me.
Well, in the first presentation on Whisper for Jeffrey Thomas, we introduced the basic concepts on how amateur radio operators send tiny signals around the world, and when an aircraft passes through these signals, it sort of nudges those signals like ripples in a pond. And by noticing the ripples, we can figure out where the plane went. MH370 detected by ripples in the pond, so to speak. In this presentation, Whisper for Experts, we build on the basic concepts and explain how Whisper works in much more detail. Whisper is a digital mode designed to test long-distance radio propagation, and stations worldwide have continuously transmitted and logged Whisper signals since 2008. Meanwhile, 6 million signals a day and 10 billion signals in total. When an aircraft passes through one of these Whisper signals, it causes a shift in the frequency and in the signal level. So there's a Doppler shift, a slight frequency change, and there is a signal scatter, which affects the signal level. And there are 25,000 aircraft in the air at any one time, which is 4 billion ADS-B data points every day. By analyzing anomalies in the Whisper signals across many different Whisper stations, you can reconstruct an aircraft's path. There are a total of 1,932 files with 167 megabytes of Whisper anomalies just on MH370. So you can see how much data is gathered. And on MH370, we had 232 data points during the 7-hour, 44-minute flight. Whisper operates at a 1.5 kilohertz bandwidth down to minus 29 dB signal-to-noise ratio. It has a time on target of 110.6 seconds. That's the coherent integration time. And it uses ionospheric multi-hop propagation. WSPR is what we call a multi-static and multi-frequency system. Multi-static means simply it's based in several locations. There are several thousand WSPR stations around the world. And multi-frequency, it uses a whole range of frequencies between 3 and 30 megahertz. And the state of the ionosphere can be modeled using the WSPR data. Aircraft reflections can be modeled as what is called a bistatic scatterer with passive radar geometry. Multipath propagation, there can be more than one path between a transmitter and a receiver, can be resolved using the angles of incidence in the WSPR receivers. The near field path loss on a signal path is spherical. That means drops off with the square of the distance. But the far field is cylindrical, what we call a waveguide, and that drops off just proportional to the distance, not the square of the distance. And observations are captured using what we call ROC curves and Monte Carlo simulations in a Bayesian framework. These are just statistical methods capturing all of the huge amount of data and analyzing it. And MH370 detected and tracked in real time is the result of all of this data. And it's tracked to a precise crash location with plus minus 30-kilometer radius with a 95% confidence level.
So, Richard, we're talking WSPR. Perhaps we should remind the viewers what WSPR is and what it was designed for in the first place.
Yeah, well, WSPR stands for Weak Signal Propagation Reporter. Radio amateurs use WSPR to test how radio transmissions travel around the world. A radio amateur will transmit a digital message, a WSPR protocol, and then any other radio amateurs who receive the transmission will log it in a central database. As I mentioned, 6 million WSPR signals are crisscrossing the globe every day. And WSPR has grown into one of the world's largest distributed sensor networks for the ionosphere and global radio propagation. And as of today, as we mentioned, 10.5 billion individual WSPR reception reports, or they call them spots, since logging began in March 2008. So what we can do is go back to 2014 and look for MH370 in all this data. We're showing a screenshot of the WSPR protocol. The WSPR signal comprises the call sign of the transmitter, the Maidenhead grid locator of the transmitter, and the power level of the transmission. It's 50 bits of information which is sent. It is encoded in 162 binary channel symbols using what is called a forward error correction algorithm. And the 162 symbols are sent at a baud rate of 1.648 baud over 110.6 seconds. And anyone receiving the signal would then add their call sign and locator and the received signal frequency and the signal to noise ratio and any frequency drift that they detect.
So the WSPR locator is not precise enough for scientific research or technical applications, Richard?
That's right. The Maidenhead grid locator is standard 4 characters. Sometimes radio amateurs use 6 characters.
Mm.
The four-character locator, for example, FN31, has a precision of only 20 kilometers by 10 kilometers in a rectangle. And that's the limit because the Whisper protocol only has 15 bits of data available to encode the location.
Mm-hmm.
A six-character locator, which is often used by radio amateurs in logging, for example, FN31PR, has a precision of 2.5 kilometers by 5 kilometer rectangle. This is useful for most practical purposes for radio amateurs, but we need a much more accurate location. And we use the exact latitude and longitude of each transmitter and receiver antenna to 6 decimal places. And if you have a latitude and longitude to 6 decimal places, you're down to 0.111 meter error. So that is, sub-meter accuracy and well beyond what the Maidenhead grid can give you.
Mm. So you've built a database of all Whisper call signals with the locations of the transmitters and receivers to 6 decimal places. Is that right?
Yeah, and that was the major effort, quite time consuming. Um, and radio amateurs use a number of databases to find where you can find information on their call sign. And we're showing a screenshot of the QRZ.com database, just one example of many of the databases. And a typical entry in that database is the call sign VA7HC, which is a contact of mine in Canada. And his Maidenhead grid locator is CN88HK. But the database actually gives his latitude and longitude exactly.
Mm.
And we built a database with around 10,000 Whisper users, just a little over 10,000. Some of those are mobile users. The transmitter is on a boat or a car or even on a balloon. And so out of the 10,000, 941 are mobile, but 9,325 are static. And we use the static Whisper users because we like to compare signals from the same transmitter to the same receiver in the same locations over time. For MH370, we used 4,153 Whisper users globally. And we check the source of the data that we use in many different ways. So firstly, we check the latitude and longitude match the Maidenhead grid code. That's a simple algorithm. And then we check the address given in Google Maps aligns with the latitude and longitude. Some call signs have multiple locations. They have a home address, an office address, a weekend place, or a holiday place. And they sometimes take their Whisper system with them, or sometimes they have multiple systems all using the same call sign. So we carefully check that in the database. And some will even use a microwave link to a remote repeater station. So their Radio Shack is in their back garden, but they have a repeater to an antenna sitting on top of the mountain 10 kilometers away. So we take that into account. So it's quite a interesting piece of work to get an accurate antenna database. But the result of it, we can compute great circle paths to less than 1 meter error. We can derive takeoff angles from the transmitter and work out the antenna pattern analysis. And we can work out exactly where any multi-hop ionospheric propagation lands on the ground or the sea on its route around the world. And you even have a topographic database to see whether when it lands on the side of a mountain or whether it's landing on flat Earth or relatively flat ocean. So there's a lot of work goes into this system.
Yes, indeed. Absolutely. So, Richard, in a previous Whisper episode, you said that these weak radio signals can easily travel around 20,000 kilometers or more to the other side of the world. So, how does that work?
Well, that's what we call ionospheric propagation. Excuse me. Radio waves can bounce off the ionosphere by refraction, and they can be reflected and bounce off the ground or the seas. So they go around the world in several hops.
Hmm. So, what is the difference then between reflection and refraction?
Well, reflection is just bouncing back from a surface like a mirror. Refraction is when light or radio waves is bent through a medium change. I think we've all seen when we put a straw in a glass, it looks bent. And that is refraction because of the change of the medium between the air and the liquid in the glass. Early radio scientists thought HF signals, high frequency signals, bounced off the ionosphere like a reflection from a mirror. But in reality, the ionosphere's electron density changes gradually with height. And if the angle is right, radio waves are bent continuously back towards the Earth. There is a critical angle, and when that's reached, radio waves don't come back towards the Earth, they just go off into outer space. So, ionospheric reflection, as it's called casually in ham radio amateur terms, is technically refraction in a plasma gradient. For a given ionospheric layer, there's a maximum frequency, the critical frequency, where radio waves will still be bent back towards the Earth. And above that frequency, or at too steep an angle, the waves will then escape into space.
Hmm. What effect then does the ionosphere have on the radio waves?
Well, a massive effect.
Yeah.
High frequency radio waves, typically 3 to 30 megahertz, can be reflected or more precisely refracted back to the Earth's surface, but you need the right frequency and the right angle. I'm showing a screenshot of the ionosphere layer by layer and daytime and nighttime. The ionosphere is a region of the Earth's upper atmosphere which is ionized by solar, ultraviolet, and X-ray radiation. There are several layers at various altitudes with different ions creating different effects, absorption, reflection, and refraction. So it's a very complicated mathematical model to model the ionosphere. And these layers change between day and night. And there are special effects at dawn and dusk, which is called the gray zone or the gray line. And on top of that, radio amateurs are interested not only in the weather on Earth, but in what is called space weather. There is a 11-year solar cycle, which makes a huge difference month to month. And there are also sudden changes with solar flares and geomagnetic disturbances from coronal mass ejections, CMEs they're called, and geomagnetic storms can affect the ionosphere minute by minute. So the sun has a huge effect on the ionosphere. And on top of that, there are things called TIDs and SIDS. A TID is a traveling ionospheric disturbance, and a SID is a sudden ionospheric disturbance. And TIDs are gravity waves that cause fading of radio signals and Doppler shifts and distortions, and they can last minutes or hours. And SIDS are sudden bursts of solar X rays or gamma rays that cause HF blackouts, strong absorption rather than refraction, and that can last seconds or minutes.
Wow. So this begs the question, how does WSPR cope with all these dynamics?
Well, that's the beauty of WSPR, and it was designed by a guy, Professor Joe Taylor, and it was designed to cope with exactly this kind of unstable, noisy, and constantly changing propagation that the ionosphere throws at us. WSPR has a very narrow bandwidth. It's only 6 hertz wide. And narrow signals need much less signal to noise ratio to be decoded. And we successfully decode down to minus 28 or 29 dB SNR in a 2.5 kilohertz bandwidth, and sometimes even lower signal strengths. And it has this forward error correction. So the 50 bits of information are convolutedly encoded and interleaved with 162 symbols. And this adds substantial redundancy so the decoder can recover the original message, even if some bits are lost due to fading or noise or interference. It also has a time synchronization. There are 2 minute slots, and that starts signal transmission at every even minute plus 1 second, and it's aligned to UTC. And most decoders use a GPS synchronization to keep the clocks precisely synchronized. It has, as I mentioned, these robust decoding algorithms. A WSPR decoder actually uses a fast Fourier transform, FFT, to analyze the received signal. And there is a huge strength in statistics from the network because there are literally thousands of simultaneous transmissions and receptions, WSPR receptions worldwide at any point in time.
Yeah. So is WSPR used in research now to better understand the ionosphere?
Yeah, it's in huge use for this purpose. And scientists have been researching the ionosphere for the last 150 years. So we have a lot of data gathered. There is a model called the International Reference Ionosphere Model, IRI, and we use that model. But that has basically monthly historic mean data. What WSPR allows us to do is to know the state of the ionosphere every 2 minutes. So we use WSPR to determine the state of the ionosphere at each point in time, every 2 minutes. And we then use WSPR to detect and track aircraft based on that knowledge of the ionosphere. So it's a twofold process. And aircraft scatter or reflection can produce anomalies in these WSPR spots. And you can pick up data on a non-line of sight path. So you can see an aircraft at anywhere along the WSPR signal path around the world. And by combining precise transmitter and receiver coordinates down to the nearest meter, you get great circle propagation modeling, which is very accurate and can isolate signals which are affected by an aircraft. We're showing a screenshot of the ionospheric whisper propagation and aircraft detection. And this has led to a passive radar-like technique where aircraft can be tracked even when their transponder is switched off, as was the case in MH370. Once the transponder is switched off, you don't have any ADS-B or any secondary radar data. And it's essentially like doing an MRT scan of the ionosphere. An MRT is a tomography, and this is using WSPR as a ionosphere tomography, if you like. And that helps us to narrow down exactly where aircraft are and enables us to detect them and track them.
But with 25,000 aircraft in the air at any one time, how do you tell which aircraft is which, and how do you target a particular aircraft like MH370?
Yeah, well, the first Whisper experiments were conducted using flights to the Antarctic. And the reason for that is because there were relatively few aircraft and they were well spread out. But what Professor Simon Maskell at Liverpool University did was download all of the ADS-B data for 100,000 aircraft over a 24-hour time period. And he then also downloaded all the Whisper data for the same 24-hour period. And he uses a large computer network to compute every aircraft track and every whisper propagation path every 2 minutes. And you can see there's a huge amount of data and processing power involved in that exercise. You can do it on a laptop, but it probably take a run, a simple run, all night long, so you get the results the next day. What he does, of course, is almost in real time because he's got a much bigger computer. And you can then predict where an aircraft is likely to be 2 minutes into the future and predict which whisper signals will be affected. And you can check back 2 minutes later and see if your prediction was right and update your results in a Bayesian framework. Essentially, a Bayesian framework predicts what will happen next based on what has happened before. And at its core, you have what is called a prior, what you believed before your initial probability distribution based on what has happened up until that point. Then you have a likelihood, how consistent the new evidence is and what the different possible outcomes are. And you have a posterior, which is when you update what you've previously seen with the new evidence, and you then start to predict what will happen next. The ionosphere is noisy and uncertain, and aircraft scatter signals are weak and can be masked by natural variation. So a Bayesian filter allows you to combine your prior knowledge, ADS-B trajectory and the propagation physics. It allows you to incorporate new observations from Whisper every 2 minutes and produce a continuously improving probabilistic track of the aircraft. The method basically Whisper plus ADS-B plus Bayesian inference turns your system into a global passive radar system that doesn't transmit itself but continuously scans the atmosphere and validates itself every 2 minutes.
But of course,
Sorry. Too much talking, dried up.
That's all right.
Sorry.
Yeah. But Richard, those viewers who are still with us and sharp will be saying to you, there's no ADS-B data available for MH370 in the middle of the Indian Ocean.
Exactly. So we use WSPR and the Bayesian inference to track an aircraft. The DSTG in Australia published a book and an academic paper called Bayesian Methods in the Search for MH370. That came out in 2015. And what Professor Simon Maskell did was he actually helped with that original Bayesian framework, but he then add the WSPR data into this model. And where we do have ADS-B data, we use that to check the model. And when we no longer have ADS-B data, once you're out of range of Malaysia and off into the Indian Ocean, we then use WSPR to predict from the last known aircraft position going forward in time every 2 minutes. And the Bayesian framework combines the last known radar and ADS-B data near Malaysia. It combines the satellite Inmarsat data, the so-called handshakes or pings. It also combines the ocean drift modeling and the debris finds, and they all come together in a huge system. And these data sets allow us to double check the results. I'll give you an example of how this works, not using MH370, but one of the 100,000 flights that we tracked on a single day. A KLM 646 flight from New York to Amsterdam. The flight route is shown in the screenshot as it crosses the Atlantic from New York to Amsterdam. The bold black lines are where we have ADS-B data and also WSPR data, so we can combine and check. The thin line is where we only have WSPR data. And so the workflow is use ADS-B data to train and validate your WSPR-based detection where that data is available and abundant. And then you extend the Bayesian inference framework into the ocean gap where you've only got WSPR data and you no longer have ADS-B data. And you continuously update the aircraft trajectory from the last known position.
So, Richard, some critics have said that WSPR signals are too weak to be used as a global passive radar system and cannot possibly track MH370 in the middle of the Indian Ocean.
Yeah, well, that's true, and they have made that criticism, but it's based on the radar equation of short distances. Radar typically works out to 100 or 200 nautical miles, and the path loss on that kind of a system over a short distance is to be compared with the square of the distance. So the path loss increases with the square of the distance. However, Ionospheric, as I mentioned earlier, works differently. In the short and the near field, it is spherical, so it's the square of the distance. But in the far field, it's cylindrical. It actually works as a waveguide, and it's not proportional to the square of the distance, but only to the distance. So our multipath measurements in the frequency range 3 to 30 megahertz show the expected waveguide results. We're showing another screenshot of the KLM 646 position with WSPR anomalies and a global map. And on the global scale, we can see where the WSPR transmitters and receivers are located And these are the ones showing anomalies at this point in time in the signal level and the signal frequency. And the whisper propagation paths all intersect at a particular location near the east coast of Canada during this flight. And showing another screenshot, zooming in locally to this area, and you can see that the intersection point matches exactly the ADS-B data of KLM 646 at that moment in time. And we know the ground speed and the track of the aircraft from the previous detections, and we can then predict where the aircraft is likely to be in 2 minutes into the future. And when the aircraft finally leaves the coast of Newfoundland and there's no ADS-B data because it's then out of range, we continue to track with the whisper detections every 2 minutes until it reaches Ireland or near the coast of Ireland and the ADS-B data comes back on. In the case of MH370, we track until there's no more ADS-B data, and then we track only with the whisper data every 2 minutes, and we continue that tracking until there are no more whisper anomalies to be seen. And that is when MH370 crashed. So we are able to track MH370 all the way to the crash location.
Yeah. Well, that of course is what the new search is primarily based on, is it not?
Indeed.
Yeah. So yes, well, Richard, I just that's just amazing, extraordinary science there. I'm glad there's not a third episode for a Whisper for extremely intelligent people, because I'd have to get someone else to compare it. Amazing stuff, and thank you so much for doing this as a prelude to the search for MH370 resuming. And the other thing that's going to we'll really look forward to is the 10 things that we need to know about Whisper for the search for MH370. That'll be well worth looking forward to.
Yeah.
So
And if viewers do want to take it to the next level, I mean, they may be academics or researchers, then I'll very gladly have an email and I can do two things. One, give them a list of all of the academic papers currently available on this subject, and there are quite a few, which is interesting reading for an academic. And the other thing is we offer the whole software. If you have a MATLAB license and familiar with using MATLAB for this kind of research, then you can set it up yourself and try it out for yourself in your own lab or office.
So, viewers, thank you very much indeed for tuning in today. Please subscribe to us. Please like us. Please do join us. We'd certainly appreciate your support for responsible journalism. Please keep those wonderful comments coming. They're fabulous. And keep those great questions coming. We do appreciate them very much indeed. And Richard, once again, thank you for your amazing work on this Whisper for Experts. I really appreciate it.
You're very welcome.
And viewers, we look forward to your company on Saturday, and please do have a good weekend. Thank you very much.